I've been working in the Amazon for about 15 years, and since 2005 we've been working with a diverse group of scientists from the US, Brazil, Europe on many of the issues regarding agricultural transformation of portions of the Amazon. The Amazon is, portions of the southeastern Amazon have been converted into pasture land and row crops over the last 15 years or so. And it's had a very large impact on many aspects: hydrology, carbon, nutrient cycling, and this is where I've been working with Jillian on some of the nutrient issues. My particular passion is in the hydrology, so I'll talk a little bit about what we've been doing in the southern Amazon in particular to try to understand the changes in the hydrology that occur, and they, from various spatial scales, from farm field scale to millions of square kilometers. Changes that occur at very different scales, and they're complex because of those different scales. So I'll just show a few examples of what we've been doing there over the last, since about 2005 is when we started in the southern Amazon. So I'm going to talk about the Amazon in general, just to give a broad overview of the big system that we're interested in. Talk about some of the issues driving deforestation and degradation, and then show some of the energy and water balance changes that are occurring. The basin this is the Amazon basin itself then, so this is about 6.5 million square kilometers. And it's shown, this is a percent tree cover in 2010, so you see this region in here, which the orange line separates the tropical forest biome, the evergreen forest biome, from the Savannah biome. So you see in this region here where the deforestation has occurred in the last, let's say, 20 years. For scale, just throw that up there. It's roughly the size of the continental United States. We talk about scale, and it's one of the real issues with the Amazon. It's big, and big. This is 800 miles from the ocean, at Manaus, and it's actually the Rio Negro, which is one of the tributaries of the main stem of the Amazon. It's big. In this location, it's 200 feet deep, so it's big. And I show this. This is the discharge in cubic kilometers per year of the Amazon and the top 10 rivers of the world. And you have to add up all 9 to get to the Amazon. You add up 9 other largest rivers of the world. It's about 20% of the entire river runoff on the planet. So it is a big river. And this is just a map showing, basically, that's what I mentioned before, potential vegetation. It's, in the broadest sense, it's tropical evergreen forest over the vast majority of the basin, and then there's a Savanna region in the south. And that follows the precipitation. Basically, there's less rainfall in this region and a much longer dry season. This region has a 5 to 6 month dry season where I'll talk about the region here, they get almost 2 meters, we get almost 2 meters of rain a year, but it all falls in 6 months. 6 months, there's no rainfall whatsoever. So it's very strong. So to get a quick transition from forest to savanna. And just, basic environment. Tropical evergreen forest. And within the forest itself on the ground. Just, dense vegetation at all levels. And a typical stream in the forest. Very clear water, sandy bottom. Very typical of an undisturbed stream in the forest realm. And a somewhat larger stream. This is near where our field work is done. Actually, it's on the farm where we do our field work. A typical sort of palm swamp river. So looking at this, so the savanna then, I'll just show a few pictures of savanna. This is an overflight of the savanna just to about in here. And individual trees spaced very evenly depending on the water availability. And that's a typical ground shot. During the wet season, this is pasture and scattered trees. And a larger river, the Ecological is showing mostly drought deciduous environment in the Sahara, whereas the evergreen, not deciduous obviously. So drought deciduous forests, large river systems. Currently about 17% of the entire basin, if we add it all, about 17%, 15% is deforested. mostly in this region here. When we look at what it's turned into, majority of it's cattle ranching. And this is a typical dry season shot of the cattle ranching. You know, this is in the evergreen forest biome. So they left one tree that was now dead. But that's a pretty typical shot in the dry season. It's been 5 months without rainfall, and without trees, it just dries out immediately. Cattle ranching, probably 80% of the deforestation is for that. The other is industrial agriculture, and this is becoming increasingly important. This is something that Jillian and I have been working on a lot. This is a soybean field on the ranch where we work, typical scale. They might be 10 kilometers, the fields might be 10 kilometers long by, you know, they might be 10 by 10 block or something like that. Dry season, right before planting, and then middle of the wet season, January, during planting, you know, after planting. It's fruiting now. So, oh, and this is a shot then of, this is an aerial shot. This is kind of a typical shot of a mosaic landscape. We've got a rubber plantation here. A lot of farms put that on there as just extra income. They'll have a small area of rubber plantation. You've got a riparian forest that they've left alone. We have a soybean field here, pasture here, and this is felled trees. They're all in rows, drying out. They will burn this. They have since burned this and turned it into soy. So that's very typical look at the land uses that occur there and the transitions, how they're done.
And that used to be original forest?
Yes, all of this was this, you know, evergreen forest. This is a movie of deforestation that I took from the truck window. But basically what they do is they've got a giant chain hooked to 2 tractors and they just tow it and they mow the trees down. Yeah, and they mow it all down, they leave it in rows, they dry it, they burn it, and they burn it several times until everything's gone. And they do this on a very, so that, the aerial shot I showed of those trees in rows, that's how they did it. They just literally a mowing process. The other degradation issue that comes up in these forests is fire. These are hot pixel, this is just a collection of hot pixel shots for the Amazon for I don't know which year this is, but it just shows fires occur where humans are. Fires in the evergreen forest are not a natural process, they just don't occur. So they occur where humans occur and it's a land management technique. And they often escape into the, so they'll burn the pastures every few years to regenerate the grasses. And they often escape into the forest. And this is a typical understory fire, which we actually lit, because we have a very large experiment where we're burning the forest in these blocks to see what in fact dies, what grows back, what ecological transitions occur when you put fire in the environment. But it's a very typical fire. They're very low stature. They're only about like this, and they move slowly, but they kill the trees very effectively. The trees are not fire tolerant, very thin bark usually, so the cambium layer heats up very rapidly. So 1 or 2 of these fires can take out a huge amount of carbon from the forest, you know, through mortality. And this is it's used by farmers as a pasture maintenance technique. It's also used by the native populations. This is one of the very large indigenous reserves within the area where we work in the upper Xingu River. And this is all smoke. And they light fires routinely to open the forest up. This is in the Cerrado, it's in the Savanna region, but they'll use it as a tool for hunting, you know, basically.
And half a millennia?
Half a millennia. It's a typical technique, and that's just a close-up. You see this big arc of fire right here. So burn them and just let them go. And that's a shot of where we work. This is actually, these are experimental fires. You can see the dead trees in here. That's where we burn the forest to see how it compares to unburned and what occurs. But typical shot of this forest, and this is now soybean landscape. There's a big change that occurs in the energy and water balance when you go from this to this. And a healthy evapotranspiring forest and a very static landscape. There's really no water transfers occurring in the dry season. So I'll talk about that a little bit. And this is my little cartoon schematic of the water process. Basically, water vapor is coming in from the Atlantic Ocean, for the most part. Some of it goes out downstream. Some of it falls as rain. 2/3 of that, roughly, goes back as evapotranspiration over the forest, and 1/3 goes out as river flow. And that's pretty much where it's standard in the forest. If we chop down our tree, we reduce the evapotranspiration. That's the first big change. And that causes, basically, an increase in the outflow. Rainfall isn't affected at the local scale, usually. So you just get this pretty simple change in the water balance. And we've been working at this particular ranch in the south part of the Amazon to quantify that, to see just how much of this occurs and on what kind of scales. So basically, decreased evapotranspiration occurs because you have less leaf area with the crops or the pasture that replace the forest. You have much shallower rooting depth. The trees go down 10 meters. They're easily using water at 7 meters during the dry season. The crops only go down a meter, meter and a half, and nothing at all in the dry season. And canopy interception, actually, I should take that off there. We found out that canopy interception in the forest and the soy are incredibly low. Less than 8% of the rainfall that comes in is actually intercepted by the canopy. That was something we had set up as a series of experiments. So I should take it off. It's really just, the changes that occur are really these transpiration issues that occur. Flip side of it is, you've taken the forest out, if you're getting less ET, oops, sorry, getting less ET, what you're getting is a lot of sensible heat flux. So now instead of the water vapor taking the radiation off the landscape, it's sensible heat flux. This heats up like a frying pan, and dust devils form. That's just a typical, you're just seeing the heat being sent up the atmosphere. And this is a movie of that dust devil, just because we were out there. And again, this was evergreen forest, all of this.
So what state is this actually in?
This is Mato Grosso, so center Brazil. And that's just a dust devil. And that's, it's just illustrating that what you've got is a huge sensible heat flux, where you previously had a latent heat flux. And it's trying to get that, the radiation is coming, the sun's the same amount of radiation is coming in, but instead of taking it out as evapotranspiration, it's taking it out as sensible heat flux now. So we have a big experimental station here, right on the border between those. It's in evergreen forest, but it's right on the border with the Sahara. It's in the Xingu River Basin, large indigenous park in the center of the basin, farmland and forest around Green's forest, and obviously these are the farms embedded in the forest. So a lot of issues going on here with changing this landscape, the fact that the native populations are downstream of all of this. So there's a lot of social and physical science issues here that we've been interested in studying. This is the ranch. It is, zooming in, this is a landside image of it. It's an 82,000 hectare ranch. So that's 200,000 acres.
Yeah.
Yeah, 200,000 acre ranch. Roughly half of it was deforested originally as cattle pasture. It's now all been converted to soy. It's been in soy since 2005 through 2008 is when they finally got down here, conversion. They're now planting a second crop of corn in the north. After the soy is harvested, they put a corn crop in. That's just started recently, and that's what Jillian and I are trying to look at now. And this is a relatively large ranch, but it's typical. There's a ranch to the north that is 160,000 hectares, so that's 400,000 acres. That's now just converted to soy. So the farming there is on a large scale. As everything. So again, it was broadleaf evergreen forest, roughly 25-meter in height, canopy height. So it's a short stature forest because it is a drier region. It has a long dry season, but it's still the same species that exist up in the wetter north.
Do these farms make some effort to comply with like the legal reserve and the environmental protected areas?
They do. And this one we've been working on, they try hard because they're a very visible company.
Yeah.
So they get a lot of...
And the legal reserve there is about 50%?
The legal reserve is 50% now. It was 80%, but they were grandfathered in because it was deforested originally in the 80s, so 50%. So they cannot deforest anymore. And they've got a lot of riparian forests that need to be restored. So we've been doing a number of different experiments from satellite, looking at it from satellite to try to quantify the water balance, to we've got soil pits, we've got resistivity measurements where we put out electrical probes to look at the soil moisture. We've done been doing a lot of different experiments throughout this ranch for eight or so years. This is a zoom in of our burn experiments where we have 3 50-hectare plots. We burn 2 of them, one every 3 years and one every year, and one not at all. And then we look at everything from changes in carbon, nutrient, and water that occurs when you do this. We're not burning any longer. They have been burned enough, and now we're looking at regeneration and regrowth, how it naturally occurs. In terms of satellite, one of the things I've been looking at lately is the MODIS. There's a MODIS product available that measures the evapotranspiration. It's basically a modeled evapotranspiration from satellite observations. It's a nice data set. So we're looking at the differences in evapotranspiration as seen from satellite over the soy and the forest. And with the MODIS, we can look at pure pixels that are either soy or forest. We can basically, we have 80 pixels of each. We add them up. We take a mean just to see what the difference in evapotranspiration is. This is trim rainfall for the ranch. For this ranch, January peak in rainfall. Very, very little in the dry seasons. This is surface temperature. Forest is green, soy is yellow. It's 5 degrees C hotter in the soy than it is in the forest on the annual mean, and the seasonal cycle is more than double, almost triple. So it's hot. That's the key. You've got mean monthly temperature of over 40 degrees Celsius in September. It's really hot.
Wow.
Yeah.
What's the growing season on that graph?
So the growing season, they're planting in November now in order to get a second crop in. Okay. That rainfall shows you this is the growing season. October, rains can be very spotty, but they're planting in late October now if they want to get corn in. And so if the rains don't come, they don't put a second crop in. They'll make that decision. So that's the, I won't go into details of that, but basically we're looking at these products and seeing what it looks like. Evapotranspiration, green is evapotranspiration in millimeters per month. The forest, green is the evergreen forest. So basically 110 millimeters per month, clear into July. And only in August, September, and October does it really fall below that. So it hasn't rained since April. It's still evapotranspiring at a maximum rate. So it's taken soil moisture out, is what that tells us. And comparing forest to soy field, you see this soy peaks right here in the middle of the growing season and then falls off to values below 50 millimeters a month is what it's calculating. So big difference in the amount of water that gets back to the atmosphere. And when we look at the numbers, it's basically a 30% reduction in the amount of water that goes back to the atmosphere when you replace the forest with something else. And I can go into details a little bit, but at this site, they switched from pasture to soy over the course of the period from 2000 to 2008. And it looks like soy has more evapotranspiration than pasture if you looked at the timeline. So there's a climate signal in there, obviously. So we tried to remove the climate signal by just looking at what we knew in 2006 and 2007 were soy and pasture, and comparing those. And the bottom line was the pasture consistently has less ET than the soy in the early part of the season, and more in the late season. And overall, there's a significant decrease. There's significantly less ET over pasture than there is soy. So pasture has the least amount of evapotranspiration occurring of these land uses that they're applying.
And that's just open pasture?
Open pasture, yeah. Yeah, there were no trees on that, in those pastures. So we look also at the soil moisture. We have these, we have 9 soil moisture pits that are 6 meters deep. And so this is a picture from the bottom of the pit looking up. And that's, the soil is this oxisol, this tropical clay sand mixture, and it's beautiful stuff. I mean, it's absolutely uniform. They dig these pits and the corners are 90 degrees, and they're just flawless. And then we instrument it with water content loggers at every meter to just have continuous measurement of the soil moisture. And that's Darlison, the leader of we have a team of at the moment, about half a dozen guys that live on the ranch 5 days a week and collect data for us. Basically, install instruments, fix instruments, collect data. And he's the team leader, and he's downloading the soil moisture data at that point. And this is soy field in the dry season, and those are the emmas that have the RIA, yeah. which is a Cerrado bird, but they've invaded into this region because
So they did that on their own?
they did it on their own, yeah. Yeah, it's opened up, and so it's a great environment for them. So they've taken advantage of this new environment. And they're very populous. So this is soil moisture with depth from 0 to 10 meters. Water content millimeters per meter of soil. And what it shows is the soy has more water in the soil below this 1 to 2 meter level, which makes sense. The forests are using this water. And this is the annual mean. So the forests use more of the water below 2 meters. Soy doesn't have any roots down there. And we wanted to see that because we really, it makes intuitive sense, but we never could say that quantitatively. And basically, it's maybe 15% less water in the forest than the soy. And that's just a difference between September and January. So it rains in January, rains till about April, then it stops raining. And what this shows is if I take the difference, the forest has used up that water in that level, is what it says. Whereas the soy, it's sat there. There's the difference between the 2 months is maybe 25 millimeters of water, whereas it's 75 here. So the forest is taking more water out of that layer of the soil. We've been doing resistivity measures, so we lay out a cable with probes and shoot electricity randomly to measure how resistant the soil is to electrical conductivity. The more resistant it is, the less water is in the soil, basically. And so what you get with that is these really lovely pictures. This is a 320 meter transect from the forest into the soy field, going down 15 meters in the soil. And that's December, so it's in wet season, and it shows forest is relatively wet. There's a break there, that's soy, and it's very, very wet. Blue is wet. So same amount of rainfall is occurring here, same amount of through-falls occurring. They're both basically all the rain, 92% of the rainfall makes it to the soil surface. But in the case of the forest, it's being pulled back out of the forest for evapotranspiration, and it's not in the soil, so it ends up in the soil. So again, this is something we really wanted to prove, and this particular tool has been good for that. This is July, middle of the dry season. You see very much drier in the top 4 meters in particular in the forest, and still very, very wet in the soil. So that water has entered into the soil column and is slowly making its way out in the soil. And in the forest, it's going out this direction instead of that direction.
So baking sun doesn't dry out the surface in the soil and draw water back up to replace it? And
not on a giant scale.
I see.
Surely there must be some, but we're not measuring that. And it's not a big part of the budget because when we look at the discharge in the rivers, and this is Shelby Hayhoe did this study where she looked at discharge in streams exclusively in soy and streams exclusively in forest. And bottom line was soy is 4 times greater than the forest. So that water that got into the soil is now just being transported out into the river system. And that's consistent on all these streams, and it's something we'll talk about a little in a minute. And in these particular forest sites, you see the actual discharge is pretty small. There's very little discharge. It's a pretty dry region. So the trees are using most of the water that arrives. So, the bottom line is that at this scale, in these farms, you've got an ET change about 30%. You have 30% less here. You've got a big change in soil moisture. It goes into the soil and it comes out in the streams and it's shipped off into the ocean. You can show that pretty clearly from all the different levels. And when you think about that integrated across the entire river basin, it's a significant change. This is the evapotranspiration product just shown for 1 year, and it's just illustrating that you've got a high evapotranspiration here and low anywhere it's been deforested. And if I did a back of the envelope, I'd expect maybe a 10% increase in discharge of the river here. That's just back of the envelope, but I don't have any of that data.
Or you're also not looking at, deforestation elsewhere is reducing the rainfall that comes in from elsewhere. Right?
That's a very big possibility, and that's something I'm going to talk about.
Right.
Although I see I'm running late, so I'm going to kind of. But that's something we really want to know.
Yeah.
We don't have any measurements here to show that this integrates up. But we did at another location to the south. This is in the Cerrado, the Araguaia Basin. I mean, there's an 82,000 square kilometer basin down here. Here's the ranch where we work. It's this one. We had good discharge data there. So we were able to look at this. It's been about 50% deforested, although it looks like a lot more than that in this image, and I never quite rectified that. But, basically, there's been a couple of studies by a colleague of mine who looked at large changes in morphology of this river. Clearly, with the deforestation, they see a huge increase in the amount of sediment in the river. This has all been laid down in the last 40 years. All of this sediment in the floodplain. The river has changed its shape. It's now much straighter, deeper, more V-shaped, basically. It rearranged itself to get rid of the sediment. So we were then able to look at the discharge of that river. This is the river itself. We were able to look at the discharge data and say, okay, was there a comparable change in the discharge that occurred in this period with the deforestation? And when we looked at the 2 decades, 1970s versus the 1990s, we saw a 25% increase in discharge occurred in this river. We had no statistically significant change in the rainfall. There was a 2% increase. So it suggests that, for that to balance, you have to have a 4% decrease in evapotranspiration to have occurred. Naturally, that doesn't seem very reasonable given that the rainfall increased. And this is a water-limited region, so I think if the rainfall increased, the ET would increase. So this doesn't add up in terms of, unless you do something else like deforest. That was our conclusion. To kind of back that up, we went ahead and we did a series of numerical modeling studies where we modeled the system and asked, okay, which of those 2 scenarios makes sense? Is this a change in climate-driven ET change, or is it a change in landscape? We use a numerical model, which I will now gloss over entirely. But it's a dynamic vegetation model is one of several that are used in conjunction with climate models and those things. We'll talk only about the details of that if we want to. Raster-based, each grid cell is some representation of that location, vegetation, soils, climate. It's trying to represent this actual system. What it's trying to do is show canopies, soil moisture use. Basically, you've got incoming radiation, and the model is simultaneously trying to calculate the CO2 balance, the water balance, and the energy balance. So it's growing vegetation as a function of the availability of sunlight, water, and carbon. The residual of that is your runoff and baseball. So it's trying to repeat nature. So what we did was just ran a series of simulations, one where we didn't change the land cover, we left it in the 1970s. Consistent, we used the actual rainfall that did occur, but we left the land cover alone. And the second one, we changed the land cover to today. So the difference between those 2 simulations should be the climate and the land use. And zipping through that, what we see is the model has a bias, so it's too dry. But I'm going to say it's a bias and say we're okay. The bottom line is, if we don't change the land cover, then we get a 9% increase in discharge. So that 2% precipitation increase leads to a 9% discharge increase. If we do add land use, and our correlation decreases. So the simulation is diverging from nature, is what it shows. And if we do add the land cover, then we get a 27% increase in discharge, or 29% increase in discharge. So with the land cover, we get something that looks like what occurred. Without it, we don't. And that was the bottom line of that. So at this large scale, it appears that 2/3 of the increase in discharge that we've seen in the last 40 years is a result of that deforestation that occurred. And 1/3 is probably this climate change that occurred also. So that's the scale of the changes that occurred and probably the reasons why it did. So that explains a lot of them. Not only do you have more erosion occurring per unit discharge, but you have more discharge. And so the river's changing accordingly. So that's at the medium scale, that's 82,000 square kilometer basin. But as you pointed out, at some point we would expect that if you have large deforestation, you're going to affect the climate. The rainfall will. If a third of the ET is now going out to the ocean instead of back to the atmosphere, the rainfall should change. So we ran a series of coupled global climate model and land surface model experiments to see what kind of scale change that would be. And we looked at, this is the present day distribution of forest. Yellow is agriculture, white is savanna, and future scenarios where a portion of this is deforested based on various assumptions about governance that's occurring there. And this is a good governance. We could say we're about 35% of the basin is deforested by 2050, and a poor governance where more like 60% is deforested. So we ran those simulations to see what kind of effect it had on climate. Basically, we left off here. We decreased ET and we increased river flow. Well, at some point we decreased this, and something occurs here. But that's the difference between this, and so it can be really complex. It could be positive, it could be negative. So we ran these suites of simulations with this governance, with business as usual, Ricardo was calling it, with modern, with potential. This is our modern simulation. This is the difference in discharge that occurs in each one of these large river basins throughout the Amazon. So we ran for the entire Amazon. This is what occurs with no climate feedback. So we just said, what's today look like compared to if no deforestation whatsoever would have occurred? Well, we should see about a 25% increase in discharge is what that says, which is in fact what the data shows very clearly, not just at our little site, but also at this where the star is. So suggests that in the last 30 years, this has already occurred. That 25% of this very large river basin, 750,000 square kilometers, has had a 25% increase in discharge. If we ran it with these future scenarios but didn't allow climate to respond, you'd just get an increase in discharge wherever you got an increase in deforestation. And it would be comparable in scale to the deforestation that occurred. If we let the climate respond with the climate model, it goes to this. We go back, everybody's positive because it's less ET. Now, rainfall's decreased. And you get this, some are positive, some are negative. And for me, the interesting story of these particular simulations comes down to the pair of the Xingu and the Tocantins. It's these basins here. This is the business as usual scenario of what it would look like. The Xingu has the indigenous park in the middle, and it's largely forested in this particular scenario. The Araguaia is largely deforested. The Tocantins are Araguaia. In our simulations, both of them had a 15% decrease in rainfall. They basically had the same rainfall decrease across this entire region in response to deforestation that occurred in a much, much larger region. However, the Xingu has a lot less, has a decrease in discharge in the order of 15%. Tocantins is somewhere about a 5% increase. It's approaching zero. Very different response, and it's because there's still forest here evapotranspiring. It still has some evaporative activity going on. And that just illustrates how complex those changes can be. And this is approaching actually zero, but this is very different than the discharge today. Basically, in this basin, it's now incredibly dry. There's 15% less rainfall. It's occurring in a shorter period of time. It's occurring, the wet season is contracted to an even shorter period. And so what you're really seeing is most of the water that falls is flushing out instead of even more than it is today. So it's a very unhealthy system. Equally so to this, I would say. Neither of those is good. And actually, the paper by Stickler et al. It's just about to come out. We're looking, Altamira, they're building the world's third largest hydroelectric dam on the Xingu River Basin. It's under construction now. And this is just, in those scenarios, you've got a decrease in, maybe a 15 to 20% decrease in discharge. Well, that's going to affect the power. And in the paper, she shows basically a 30% decrease in power production from what they're estimating. If you don't take into account, if you take into account the fact that we should see a change in precipitation. So, of these questions we ask, yes, the deforestation appears to be, the deforestation that's possible in the future appears to be, in fact, of an important scale for the climate of this region. And which trajectory it takes is important. A governance scenario is, in fact, better than and I didn't talk about it too much, but it is in fact significantly different than a non-governance scenario. So a synthesis of all of that is the hydrology of this region is currently changed, it's been altered, and it's dominated by this local effect, that ET effect. We don't really see much precip change. In any of the studies, there's occasional places where you can see statistically significant decreases in rainfall, but they're not huge. So we expect to figure, it's going to follow that trajectory for a while, and at some point, though, it's going to reach a threshold where you're going to start seeing a significant decrease in rainfall. Where that is, who knows? Our particular simulations are showing this at 35%, but that's one model, and those models have high uncertainty. So, and we also, we haven't even discussed the idea of climate change being layered on top of that. We just wanted to look at the forest, but you've got another big problem waiting in the wings there. So, and we haven't even begun to either look at the extreme event idea. That's where it intersects with people, is the change in the dry season length, the fact that rainfall is occurring small, shorter, much more severe events, those things. We haven't begun to go there yet, really. So, just conclude, deforestation rates have been greatly reduced in this region since 2005. There's some great studies on that. In the forested region, it's gone from 20,000 kilometers a year to less than 6. And that's because governance has actually been enforced and has worked. So there's a whole suite of tools that are available to reduce these impacts and to reduce new deforestation. But the Cerrado region to the east, they really aren't being applied. In the Savannah, the deforestation rate has actually increased in the last few years, and it's continuing to increase. There's now more deforestation in the Cerrado than there is in the Amazon forest. And these two regions are linked climatically. You get rid of the forest in the Savannah, it will affect the rainfall in the neighboring Amazon. So there are these tools, but they have to be applied throughout a much broader region than they are being applied. And that's some of the governance issues that occur in the future. Thank you.
I'm an energy guy, so I was sitting here saying, well, increased river flow, hydropower and all that, so it's really great what you did at the end. So I imagine the proponents were counting on either the same flow or increased flow,
Correct.
which your interactive models have shown it actually may drop.
Right. And what we didn't go into also was even if it increases, it's still just during the wet season. Those reservoirs aren't going to hold that. And they're already getting rid of the water in the wet season to get to the dry season.
Or if they do, they evaporate.
Right. So it doesn't, even with more rainfall, you don't end up with better energy production. And this paper by Stickler should be coming out very soon, and she does a really good job of going through those.
So can you just remind me quickly where the estimates of sort of the broadest scale rainfall come from? Is that just a scaled up version of that simulation numerical model you have?
The rainfall change that we were simulating?
Yeah.
Yeah, that was
biggest scale answer to Josh's question that you were talking about in your main talk about the big scale change in climate.
That was simulation.
Okay.
That's a 15% decrease in rainfall simulated for the model. Yeah. So that's our model response.
Okay.
Now it's not really any different than what you see in other numerical models doing it. It's somewhere in that neighborhood. The response tends to be down here because that is the climatologically sensitive region. This is wet year round. This is seasonal. So this tends to respond more rapidly.
And that response was driven purely by the land use change elements of the model. You shut everything else off.
CO2 we shut off. We didn't change it at all. We left it a constant.
Okay. So, sorry, just one quick unrelated one. Why don't you have a handle on sedimentation?
Well, because the only measures we have are on the Uruguay and that one.
Okay.
That's the only ones we have.
You have. It's not intrinsically difficult or more so? Or
It's just more difficult. Actually, there's two things. Measuring is difficult for us because it's episodic.
Okay.
And being there is nearly impossible for us. So that's troublesome. And that leads to simulating it is troublesome. If it's episodic, if I suspect where we are that it's actually just coming off the roads. It's not coming off the fields. The fields have infinite infiltration rates. I mean, basically we've measured 2 meters an hour is the infiltration rate. So it's almost basically nothing runs off the surface. So it's not coming off the farm fields. I think it's coming off the roads. Because they're all these, you know, the roads are dirt roads and
They're compacted or something?
they're compacted and they build these, you know, they build these sluices on the sides of the roads to try to get the rainwater to go off into these pools. But they are always gullying and washing out. So that's where I suspect it comes from. And that's episodic. It's really hard to do. For us.
Do you have a sense of what percentage of water storage in the forest is in the soil versus in the actual trees?
No, and that's an interesting question. We have done some sap flow and things like that, but we haven't. You know, actually, it's a good question. We did a paper with Laerci Ferreira where we tried to use Hyperion to measure the foliage content, the content of water in the actual above ground biomass. And I can't remember what the answer is.
I was just wondering if you've included regrowth in some of these dynamic models.
No.
Like, so for instance, in that image right there, it suggests that there's just this sort of progressive expansion of agriculture, and yet some of that is shifting, and
Yeah.
we know from other papers that there's actually quite a bit of secondary regrowth, and so some of these hydrologic
Yeah,
functions
so
would
this is, so
presumably recover over time.
So what we're getting is the worst case scenario, right?
Right.
We haven't put regrowth in there. And one of the studies, one of the colleagues, you know, he showed that in a regrowth location, after about 15 years, his evapotranspiration was back to before deforestation. Basically, basically the same. So regrowth is important. We don't have, that is not in there.
But regrowth really isn't happening along the
Well,
coast.
yeah, where we're working, there is no regrowth.
Maybe in the
It's-
heart of the Amazon it's happening, but there is no regrowth.
This is
on
not,
the frontier.
yeah, this isn't logging. This is, they go in there, turn it to pasture, and now it's being intensified into soybeans.
Yeah, the land is way too
It's
valuable. for
extremely
them to-
expensive land.
Yeah.
Okay,
The value's gone up a
but
great
that's
deal.
not true Amazon-wide.
No, if you're getting over in here, who knows? These are scenarios.
Right.
These are just so we can understand the scale of things that can
Sure.
occur, not to say that's what's going to occur. Yeah.
So you have a good idea with existing data how much rainfall leads to transition from Cerrado to forest. So you could know like what percentage reduction in rainfall would lead to that forest to not be able to regenerate this forest and go back to Cerrado.
Yeah, these models are dynamic. This is a dynamic vegetation model. So we can actually make those simulations and
You do?
yeah, and
Yeah.
you know,
So on that edge you're working, I mean, would like a 15% reduction in rainfall?
that's
would
going to push it.
Yeah.
Yeah, it pushes that boundary
Yeah.
northeast, northwest is what it does. Yeah.
This 80,000 hectare farm, how much is worth this farm? On average, let's say that.
I'm trying to remember what the latest price I heard. I thought it was 8,000 reais per hectare.
Yes,
Yeah.
Wow.
10,000.
Yeah.
I don't know,
So that's at least $4,000 a hectare.
Wow.
That's,
But it might be more like 5.
Yeah.
Have the prices gone up since?
Oh,
they
yeah,
moved
since
more?
2000, the commodities prices have gone through the roof since 2007.
Uh-huh.
And the land prices have followed.
I see, so it's really different.
Yeah.
Yeah.
The average size of the farms on this area is as big as this?
This one is a large one.
Yeah.
So they're anywhere from a couple thousand hectares to, there's one that's 160,000 hectares.
Yeah.
So I think 2 to
They're
3,000.
they're no smaller than 2,000 or 3,000.
No.
Like, it's not
Yeah.
profitable below 1,000,
Yeah.
so smallest would be 2 to 3, 30,
Yeah.
10, somewhere in there.
Yeah, you
It's
see
pretty
10 or
average.
12 very, very commonly. 10 or 12,000 hectares. We usually say somewhere around 10 is sort of our average. So we've got these sort of average shapes
Yeah.
we use.
So it's, most of the time, business-centered farms that come from big corporations or national or multinational corporations.
Correct. The big players are the
Yeah.
classic.
And most of the time, they're not caring about the wood, not even the cows. What most of them is have the right of property of the land. Because once you have forests, it's worth almost nothing. Once you clean up, it's just wool.
And that was the typical process that occurred. So like Safra Bank.
Yes.
It's on some really big ranches.
That's right.
And it's land. You buy it, take out the forest, put some cattle on
Yeah,
it.
and they
You
buy.
make a little bit of money, but you've got the land.
Yes,
Now the land's worth a fortune.
that's right.
Because it's great for soybeans, and that's what's occurred. So this giant one to the north, 160,000 hectares, it was cattle. It was
Yeah.
90,000 head of cattle.
Yeah,
Until 2 years ago, and they just converted it.
Yeah.
The family that owned it was from São Paulo.
Yeah.
They hired a new managing system, they put the money into tractors, and converted it. And it's unbelievable to think on that scale.
yes.
The ranch we worked, they bought 15 brand-new giant combines in 1 year. Each one was $750,000.
So
the margins
Yeah.
must be
So
fairly
that's,
slim for all these
yeah.
folks.
No, they make a lot of money. I think they make, the commodity prices are very high right now. Their labor costs are low,
Oh,
so their profit is pretty good right now.
wow.
Yeah.
But they can lose money in a bad year.
I see.
Commodities are bad, they'll lose money.
If they only crop one round, do they lose money if they can't fit?
No,
another
no, no.
second round of corn?
No.
No, they're still profitable.
Oh, yeah.
And most of them are dealing with commodities
Yeah.
for international markets.
Yeah, you know, when you drive around this landscape, it's Cargill, Louis Dreyfus, Monsanto, it is ADM. It's Cargill, ADM, Dreyfus, Louis
Yeah.
Dreyfus, and that's what you see everywhere. And
Wait,
giant sheds.
They own the land or they're
No, they own the-
seed and stuff? And-
Yeah, they own the giant brokerage systems.
Yeah, yeah.
They buy it, they
I see.
ship it out. That's the ranch we work with, they have 120,000 hectares of soy total on their ranches. They control 1 million hectares through brokering. Last I heard, it's probably more than that now,
Yeah.
through brokering. This is a big corporation.
So could I say that most is related with, you know, playing with money? Makes sense?
With-
most of this business, what I'm trying to see if is part of the Amazon, it's not, I sometimes I don't like to even say that it's agriculture because it's almost like a, you
It's
know,
a-
a Wall Street, they are gambling with money.
Well,
Most of
yeah.
them are people that are not even related to agriculture, they just,
No, this family, they just hire a new manager,
boom,
Right.
put the money into it. It's a, look, Safra Bank, I mean, these are banks that own this land.
they clean the
It's an
land,
investment.
they make a
It's
huge amount
insurance
of money.
companies.
That's right,
It's, you know, it's just land, that's
Yeah.
the value.
that's right.
So we are out of time, but thanks for coming and thank you, Dr. Coe, for explaining.